Excellent. And we're back live, back live, back live. Okay. How much did yesterday suck? Right? Just I don't know. I just thought it personally. Um, now I wasn't there. I don't know how it went. How did lunch actually work out? Did it like work out like? I guess I don't even know what to ask about it. Like, was it okay? Like, where were you guys for lunch? Okay, fantastic. There you go. Yeah, I don't know. It's just, I had to walk my second period class down to the library, and then I was just like, all right, see you, and I didn't have to deal with it. Um, it's gonna be interesting because everyone now has like a different lunch location. Oh, supposedly a different lunch location. I don't know, but we'll see how it goes. Anyway, for those of you that are in the live chat, if you would be so kind as to leave a comment, that would be absolutely wonderful, and then we'll kind of get this thing moving. Okay. So a couple of reminders moving forward before I talk to you guys about what is the expectation for today. Number one, you have a project that is due on Thursday. I purposefully had this thing due on Thursday. Signed it last week. Gave you guys some time in class last Friday to get going on it for the however, well, I think it was like a half an hour or so that I gave you guys at that point to kind of get this thing moving. If you haven't emailed me yet, of course, please make sure that you email me to get approval for those 3 cities. Check the list because I've updated the list with those who have emailed me thus far. Yeah, actually, let me just take a quick peek as to what it looks like. Just to visually give this thing, here we go. Too many tabs open today. It's here, project, and it was this one. Boom. So those are the cities that have been used so far. I think I tried to alphabetize them by state. I think that's what I tried to do. Yeah, so they are alphabetized by state. Obviously, I said no state capitals, and you can't use these states right here. But that thing is all good to go. Bring that back. Boom. There we go. Good. Now, as for today, because obviously you're still working on those projects, I'm not going to assign you anything brand new today. I would want you to focus on the projects in terms of what is due on Thursday. After that project is due on Thursday, though, I do plan on having an assessment on paths and circuits. On Thursday, probably after class on Thursday, I plan on assigning via Google Classroom the path and circuit major that I wanted to do on Euler and Hamilton. But I will not assign that until after the project is due. So because project is due on Thursday, I'll assign it after class on Thursday. So what I want to do today is kind of twofold. Number one, I want to review Euler paths and circuits. I want to review that. Get that thing off of there. There we go. So I want to actually knock out a quizzes just to kind of practice this thing up. I'll give you guys the code for it. I'm going to try something a little bit different with the setup on there with the quizzes. I'm going to try to change some of the settings, but I'll get there when I get there. But I do want to do a practice quizzes on Euler paths and circuits just to kind of wrap our minds around it. And then after we do that review, I do want to take the next step of graph theory that we've been working on. It's related to Euler paths and circuits, but it actually has to do with coloring, which is why I broke out some of the markers today. But you guys are going to be the ones doing the coloring, so it's going to be phenomenal in my mind. And I do have a kind of a video to kind of talk about that as well after I introduce the topic. So the very first thing that I want to do, as I said, I want to knock out this review, but I want to verbalize this review with you first, and then I will show you the quizzes code. I want to verbalize what is expected of you on this quizzes so that we kind of wrap our minds around it. Of course, you can use your notes if need be, but we'll kind of get there. So a couple things in regards to what's going to be on this. Again, we are just simply reviewing Euler-Hamilton. Just reviewing it right now. Obviously, like I said, I want to give that assessment on Thursday. Where are my other markers? There they are. Boom, here we go. So I didn't say it, so I'm going to say it right now. If you do not have those notebooks out and open, please do so. I completely butchered that line, but I'm going to say it like that anyway. I'm going to get the chat open. For those of you that are in the live chat right now, I'm going to get the chat open on my phone right here. Come on. There it is. Excellent. And like I said, just in case, if you have not left a comment, please make sure that you do so. So we're going to review this real quick. This is Euler-Hamilton review. Before we get to this quizzes that I would like to do, today is the 27th. Yesterday was my daughter's birthday. I didn't get any good pictures until I got home, and it was phenomenal. And I just got to show off just a little bit, just because it's my daughter. So I want to sort. No. How do I view that? I want to view the camera, but I want to view it by favorites. There it is. Just hold on. I'm gonna zoom in. Just look at her. Look at her face right there. Look, just hold on. I'm gonna flip over to the next picture. It's gonna be fantastic. And look at how she's posing right there. I did not tell. I just said, "Hey, strike a pose," and she's just like, "Okay, I'll do it." And then she does that one, and I'm like, "Oh my gosh, what is going on here?" And look how adorable. Just look. I'm just bragging right now. Look at that. She's just laughing, just casually, just going on, and then like that, just She's gonna be a movie star one day. Just you wait and see. If she's not a movie star, then I don't know what happened, but we'll see what happens. Anyway, in terms of Euler, I just want to remind you of a few things before we get to that quizzes review. In Euler paths and circuits, you are attempting, I think that was a sneeze, I'm not sure. Anyway, attempting to cross every edge exactly once. When you are doing an Euler path or circuit, you are attempting to cross every edge exactly once. That would be like the bridge problem. You are crossing every bridge exactly once. If you are doing some sort of a path, you don't have to end up back where you started, but if you do a circuit, you have to end up back where you started. Everything that we've been doing with Hamilton is the same concept for paths and circuits, but I wanted to remind you that in Euler, you are attempting to cross every edge exactly once. In fact, if there are exactly two odd vertices, then an Euler path is possible. This is one of the rules for Euler. Again, in preparation for this quizzes, if there are exactly two odd vertices, meaning a vertice with an odd number of edges coming out of it, then an Euler path is possible. The path was typically possible if you started at an odd vertice and then you finished at an odd vertice. And if all vertices are even, then an Euler circuit is possible. You're going to be seeing this on the quizzes in a little bit that I'm going to have you guys review from. But basically, if you had all even vertices, if the degrees of all the vertices are even, then the circuit is possible where you can start and stop at the same vertice, again, hitting every edge exactly once. Those were the specific rules for Euler paths and circuits. We also spent a little bit of time. Well, I mean, obviously, you know, it could be neither. Like, it's not. There are some graphs that you can't do either on. All you really had to do was figure out the degrees of each of the vertices, and then you could determine whether or not a path or circuit was possible. But then there was also the possibility of Eulerizing or semi-Eulerizing these graphs, where you could add additional vertices in order to force a circuit or a path. If you were to Eulerize, then you would create that circuit. If you were to semi-Eulerize, you would create that path. I don't believe this quizzes says anything about semi-Eulerizing. I got to double check that. But I vaguely remember something about Eulerizing. It's just basically like adding edges until you force a circuit, where you force all of the vertices to be even, let's say. It is entirely possible. Now, hold on. I just want to show you one visual example up on the board. No, actually, would that work? That could work. No. Well, yeah. I'll do something very simple. I'll do something very simple right here, just with like 3 vertices or something like that. And then, yeah. No, I got to add in a 4th vertice. Yeah, I'm going to add in a 4th vertice. I'm going to do some connections right here. Just kind of see how that goes. And then, chapow. There we go. Perfect. So, for example, right here, this particular graph would contain an Euler path. This particular graph would contain an Euler path, because this particular vertice and this particular vertice are the only ones that are odd. And it is possible. I mean, again, you got to hit every edge exactly once. I'm going to start here. You know, I'll do this in black so we can see it a little bit better. Yeah, there we go. But if I started here and go boom, and then boom, I got to hit every edge exactly once. Boom, and then boom, 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 and then boom. There we go. I hit every edge exactly once, but you have to start and stop at the same vertice. But then if I were to add one additional edge to Eulerize it, let's say. Let's see if I can do this one more time. I'm going to try and create it again. Do, and then do. There we go. Yes, okay. So if I were to add one additional edge in order to Eulerize it, let's say that I added that one additional edge. I'll do it like this. Yeah, boom, there we go. I believe I have now Eulerized it, because this doesn't count as a vertex right there. And now I can start and stop at the exact same location. I can pretty much do the same thing, except that one additional thing. Let's see, down here, and then here, and then here, and then, nope. Caught myself. Yeah. All right, I lost where I went. Boo, ba-doo, ba-boom. And then da-do, 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 da-do. Wait, how did I not get back where I started from? Ugh. With Euler circuits, if you don't do them correctly, you could end up in a corner. There are certain strategies for getting that thing done. But yeah, I'll do it one more time. I'm going to try it one more time, and if I can't do it, I'm going to skip past it. But again, that statement still remains the same, that if all the vertices are even, then it is definitely possible to do, I'll do it here. There we go. To do an Euler circuit. Let me double check here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yes, they're all even. Excellent. So let me start here. Let me start there. And I got to end up there. Okay. Let's see, I go here. And then I go here. I go here. And then I go here, 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 here. There we go. Nailed it. So it is entirely possible to do that. Just have to be strategic with how that thing plays out. You're going to be seeing these on the quizzes, in which you're just going to have to visually kind of knock these things out instead of actually drawing on the screen. Now for Hamilton, do you guys know, I don't know how many years ago it was like 10 years ago, they were considering getting rid of Hamilton on the $10 bill. Did you know that? Do you know what changed their mind? The musical. Legitimately, the musical changed the government's mind. They were going to get rid of Hamilton on the $10 bill and replace her with Harriet Tubman. But then the musical changed their mind and they delayed everything and they decided, you know what, let's get rid of Andrew Jackson. I think that's a great idea. If you know anything about Andrew Jackson, oh man. Anyway, for Hamilton, a Hamilton path or circuit is attempting to cross every vertex exactly once. So the big difference between Hamilton and Euler is crossing every edge. Hamilton is crossing every vertex exactly once. We dealt with multiple methods for optimizing Hamilton, let's say. We dealt with brute force, which a brute force method of determining a Hamilton circuit, let's say, it can work if you have a low number of vertices. Like if you only have like 3 vertices or 4 vertices, yeah, you could totally brute force that thing and figure out what is the best path or circuit to take. Typically, we do circuits because we just want to end up back where we started. You totally do brute force, but again, if you have a lot of vertices, it's not really viable. Like on your project, you could do nearest neighbor. Again, this is just reviewing this information. Nearest neighbor is, well, you have a starting location, and you literally just pick the cheapest path. Like from Barnegat, the shortest distance would have been to New York, let's say, if you were doing your project. And then from New York, you pick the shortest distance. And then from the third location, you pick the shortest distance until you end up back where you started, hitting every city or vertex exactly once. Then we had repetitive nearest neighbor, I'll just abbreviate it there, which is basically, it's exactly nearest neighbor, except you pick a different starting location every time. And you basically pick every starting location and do nearest neighbor, and then you pick the cheapest one, and then you can adjust the path to make it start wherever you want, like in Barnegat. And then there is cheapest link. Cheapest link is you find the cheapest connection between any 2 vertices, and you keep marking the cheapest connection. And as long as that cheapest connection does not break the circuit, as long as it doesn't cause a loop or exclude a vertex, then you can keep going with cheapest link. In the end, you want to hit every vertex exactly once. You do not want to double back on a vertex or leave a vertex out. That would be a Hamilton circuit. They've also referred to these, I've mentioned this in the past, they've also referred to these as the traveling salesman problem. The traveling salesman wants to hit every house exactly once, but that's kind of the way it is. You know, it's interesting. Are you guys, there is one in Barnegat. Are you guys familiar with the works of Jehovah's Witnesses? No? Do you know what they do? Okay. Jehovah's Witnesses are a denomination. They're technically a part of Christianity, but people would debate that. But that's not the point. What they do is they go in pairs and they travel from house to house within, let's say, a neighborhood in order to pass out their pamphlets and their literature about their church. And it's actually part of their mission in life that they do this, that they travel house to house and deliver information. They always go in pairs and stuff like that. In my life, I've answered the door to Jehovah's Witnesses like 3 times when I was a kid and twice when I was an adult. It's very interesting because it's like in the age of COVID and the virus and stuff like that, it's very difficult to, for them to fulfill their mission if you can't just go up to somebody's house and have a conversation while there's a pandemic going on. I mean, maybe you can, but I think people would frown upon it. But my point being, though, for the Jehovah's Witnesses, if they're going throughout a neighborhood and they want to optimize hitting every house and not doubling back on everything, they're going to have to create some sort of path throughout the neighborhood, walking path, I should say, throughout the neighborhood to hit every house and not double back on them. I'm surprised that you guys never encountered them, because there is a church right off of Route 9 off of Georgetown, the Church of Latter-day Saints. No? Yeah, it's off of Georgetown around that one development on Route 9. I don't know. Whatever. But my point is, though, that they try to optimize their paths. Anyway, okay. Let's try this review. This quiz is review. So I would suggest start a live quiz. I would strongly suggest either, obviously if you have an electronic device or your Chromebook, by all means, let's do that. I'm going to change this up a little bit on here. Number one, you will be able to see your answers during the assessment, obviously. I'm going to turn off the leaderboard. Yeah, I'm going to turn off the leaderboard on this one. I'm going to keep redemption questions in and the shuffle option. I'll turn off the memes for funsies, but I'll keep redemption questions in there. So yeah, I wanted to tweak that a little bit. So I turned off the leaderboard, kept shuffle and redemption on, turned off the memes. Oh, default timer, or see a countdown. Wait, participants see a countdown and get extra points for each question. Yeah, I'll turn that off. Nope. Yeah, I'll turn that off. So yeah, that timer's off as well. But I want to see what you guys can do with this. So, all right, continue. Boom. There's that code right there. So for those of you in the live chat, in a moment, I got to switch over my account real quick. But in a moment, I am going to put the code into the chat. Where are you? There we go. I would say hopefully you can see that code. But let's see. Join my quiz.com. Boom. And then the code is, come on. I want to post a comment. There it is. 108049. Boom. There we go. Kind of get that thing going right there. Let's see. Now, some of these questions, just so you guys know, some of these questions should literally be like, oh, that's a 10-second question. Yes. Some of these questions might take you a minute, let's say. And it's just a matter of, let's say, seeing the path or the graph and trying to determine what the question's asking. On the quizzes, if there's an image that you can't see that well, I believe that if you click on the image or the picture or whatever, it should go bigger. So just so you know, if there's ever a picture or an image that you can't see that well, if you click it, I believe it'll enlarge on the screen, and then you can go back to answering the question. Okay. If because I know there's more people in the chat that haven't joined yet. If you have not joined, the code obviously is only good as long as this quiz is going, and obviously that code will be at the top of the screen. So let's get going. Let's see what happens. Click. Oh, wait, I thought I turned that off. Yeah, I'll just leave it there then. There we go. Interesting. Okay. Unsort accuracy. Oh, she's done it. Oh, I was trying to do that one, and it went away. That's okay. Let's see what we got. So I wanted to take a look at some of the lowest accurate questions, and I was doing this one, and I tried to get something done on number 17. Let me show you what I did here, and I'm going to compare it to what the quizzes did. On number 17, they gave you this path right here. Let's bring that one up right here. See, did I get the right one? Yeah, I got the right one. Good for me. Cool. It says using the brute force method, find the optimal solution. And it looks like two of you chose ACBDA, which let me mark this down. ACBDA. Two of you chose this one, and I'll flip it over in a moment. And the other one chose ACDBA. There we go. Flip. So the ones in red are the ones that you guys chose. Oh, you can't see it. It's frozen. There we go. The ones in red are the ones that you guys chose. If I flip back to the choices right here, there we go. But in doing the brute force method, what I did was, well, since there were 4 vertices, it doesn't matter which one I start at. I'm going to start at A, and I went A, B, C, D, A, which here's the mirror one. I just reversed it. It's the same length. And then A, B, D, C, A, and then here's the mirror one. Reversed it. And then A, D, B, C, A, and then the mirror one. 2 of those choices were the mirror ones that you guys chose. 2 of you chose the last one, and 1 of you chose the first one. But yeah, the one that I did, the A, B, C, D, A, the first one that I did had a route of 17, and that was definitely the optimal solution for that one. That was interesting. All right. People running in my hallway. This one. It says, state whether you can find a Hamilton path, circuit, or neither. Now, a Hamilton path would be just hitting every vertex exactly once, which it is. I wonder if it is possible. But regardless, there is you can do a circuit here. For example, if I just went 1, 5, 4, 3, 6, 2, 7, 1, I can end up right back where I started, giving me that circuit. In terms of a path, I mean, like, yeah, definitely a path exists. But I would, the question is really weirdly worded here, where a circuit kind of trumps a path, where it's like I could go 1, 5, 4, 3, 6, 2, 7. Yeah, there's the path. I went through every vertex exactly once. Yes, but you could also finish it for the circuit, is what they were really trying to go for. Again, this was just a practice. This was just a practice one. I like this one a lot. I like this one a lot. And I'm actually going to come up to the board for this one because I want to draw on the board with my markers. The reason why is because of the direction of the path. They say, which of the following is the Euler's circuit? Now, an Euler's circuit is definitely possible, but if you check this out, if I go, now I'm actually, you know what, I'm not going to draw on the board, I'm just going to point, because you guys couldn't draw on your computer screens. But if you go K, the first one, K, L, Q, P, and then the next one says Q, meaning I'd have to go back to Q, but that's not possible, meaning the first one cannot be it. Let me go to the third one. The third one, K, L, Q, M, P, Q, O, K. I did not go through every vertex, every edge. I did not go through every edge at all. In fact, I never even hit N. In order to actually be an Euler circuit, I would have to at least go into N and leave N at some point, so it can't be the third one. None of you chose that one, thankfully. And then the last one, K, M, O, L, N, K, O, Q. Oh, it's simple. There's no P. In the last one, there's no P. And if there's no P, then I never went in and out of P. So it has to be the third one then, which I'm not going to bother to go. Well, actually, you know what? I will. I will do that in red just for the fun of it. But since the last one didn't have a P and this one didn't have an N, they were disqualified. And then this one was disqualified because from P, they were trying to go back to Q, which is not possible. So they went to K, L, Q, M, P, Q, O, K, N, L, O, M, back to K. There we go. There's the circuit. Excellent. That one was fun for me. I don't know about everyone else, but that one I liked. Let's see. And then after this, you guys did pretty good on it. Which is the only method guaranteed to identify the optimal solutions or minimum cost? Yeah, brute force is the only one that is guaranteed. Nearest neighbor does a decent job, but there are ones that you can miss. It doesn't get every single one. Nearest neighbor for this one. Let's see. Can I make that larger? I can't make it larger. Nearest neighbor to find a Hamilton circuit starting at A. What is its weight? With my calculator. Here we go. Starting at A, I would go to D at 2.1. And then from D, I would go to E. And then from E, I have no choice. I have to go across to B. And then from B, I have to go to C. And from C, I have to go back up to A. Yep, it adds up to 11. Yeah. That thing. Now, obviously, there's definitely a more optimal solution for this, but they specifically wanted you to use nearest neighbor for this particular problem. And then choose the correct term to match each definition. Lines or curves that connect. Yep, they are the edges. I kept trying to use that phrase edges. Path is the actual, like, well, what you would actually do, where the path that you would actually travel within the graph. But the lines or curves that actually connect the vertices are called the edges. In a Hamilton circuit, you must travel to every vertex once and only once returning to where you started. Yep, that is the pure definition. Travel, I'm just looking at this one that was chosen. Travel every edge. Yep, it says edge immediately, so it can't be Hamilton. Hamilton has to be every vertex. And then paths start and stop at different vertices. Technically, yes. This one, I'm going to argue this one for a second. Check this out. I really want you guys to see this one. According to this problem right here, paths start and stop at different vertices. Technically, yes, that is supposed to be the definition of a path. But one could argue that, well, all circuits are technically paths, but not all paths are circuits. So I don't agree. I should have changed this, because then it says down here, does this graph have an Euler path, circuit, or both? And the answer was technically both, even though yeah, the path is technically the circuit. The answer really should have been circuit. None of you chose that one, which is funny. But both ended up being the thing. So I don't like that question, but that's me. And then the rest of the questions y'all got right. So y'all are good. Cool. Now, like I said, your project is due on Thursday. Email me those cities if you haven't already. I will take care of that and answer any questions, of course, as well. Yeah, cool, fantastic. Now, I wanted to talk a little bit about this intervention period or whatever. But Nicole, you're still taking a senior English, right? Do they do like the intervention in that? No? I thought they would. It's a core class. It's like English 4, right? Yeah. That's weird. Anyway, for like elective classes, they're not really requiring us to do like intervention, quote unquote, per se. But there are going to be certain things that I'm going to introduce along the way. But first, I want to get our coloring on. Okay, I have a website that I'm going to send you guys to. Now, I know you're working on your phone. I'm really hoping that this website does work on your phone, though. I think it will, but we'll see what happens. I'm going to send you guys a website. This is going to slightly introduce the next unit that we are going to be covering. There we go. I think I'll start with this one. Wait, is it level 3, level 4, squiggle? Nah. Yeah, we'll do the rectangle one. Okay. Copy, and then I'll throw it into the Google Classroom. So right now I threw a link into your Google Classroom stream. So go to the Google Classroom stream and click on the link that I sent you guys. This is going to slightly introduce the next part of graph theory that we're covering. Now, this graph theory is directly related to what we've been doing, but you may not know that at first. Boom. This is an introduction to what is known as the 4-color theorem. Now, the way that this website works is that you have to color in every white spot on this graph, but you can't have the same color bordering another color. So for example, I have it set to green right now. If I filled in this and this, that would be illegal. I'm not allowed to do that because I have green and green sharing a border. And if I actually clicked check down here, well, it just says not everything's been colored, so let me color everything real quick and it'll give me all the errors. Let's see here. Color in all the blank spots. And then when I click check, it'll say, sorry, that's not correct. All of these issues are here. I have all these issues. I can't have these regions be the same color as the bordering region. So I can undo all of that and get back to the beginning or just reload the website probably. There we go, back to normal. Now, if you click this green color in the top right corner, you can actually change the color to something else. You can change the color to one of those 4 colors. Oh, Sydney said that she colored the whole thing green just for fun. Exactly what I just did. That's funny. But the idea would be that if I color this green, then I would have to color a bordering region something else, like blue. Now, what's interesting is up here, if I click this blue right here, if you see those 2 blue regions right there, technically they don't share a border. They just share like a dot, a vertex per se. So that doesn't count as sharing a border. There actually is a place, you guys probably know this, there is a place in the United States where something like this happens. Do you know where in the United States multiple states come together at a single point? Do you know your geography? There are 4. There are 4 states that come together at a single point. Oh, no, images. There we go. Boom. Utah, Colorado, Arizona, and New Mexico. They all come together at a single point on the map. It's really interesting. But anyway, back to this. I wanted to give you guys a few minutes to see if you can't fill out this particular rectangle according to those rules. Show that no more than, well, you need 4 colors. You're going to need 4 colors, and that little thing up there will give you 4 colors. It'll give you blue, red, yellow, and green. And just take a few minutes and see if you can't get it. Now, if you can get it correct, and you click the word check, it'll actually give you like an online trophy. You could enter in an email address and they can get like an online trophy case or something like that. So take a few minutes right now, see what you can do with filling in this picture, and then I'll talk more about what the heck is going on with this 4-color theorem. I'm going to try it as well. Let's see here. I want that red. And then I want that yellow. Yellow. And I want that blue and blue. And then I want that red and red. No, I can't have that yellow. I'll have that green. I was trying to avoid green. I can make that blue. I'll make that blue. And then I'll make that. I'll make that blue and blue. Blue and blue. I'll make that blue and blue. And blue and blue and blue. And then I'll make that yellow. That red? No. I can make that yellow. I'll make that yellow. And I'll make that red. And then now I'm going to do that. Red. And red. And yellow. Crap. I'll show you what I did up here. I still have one more section to color. But I attempted to try and do this thing with 3 colors. It is. It does? Ooh, I'm sorry. I don't know. It might just be because you're on like a mobile device, you know. But I tried doing this with only 3 colors. And there is a mathematical theorem which states that if you follow those rules where the same color cannot border itself, it is impossible to use less than 4 colors. You could use more colors if you want, but it is impossible to use less than 4 colors. It has been mathematically proven. It has mathematically been proven that you cannot use less than 4 colors. I tried using 3 the entire way through, but then I get down to this right here, which borders all 3 of the colors that I've been using, the blue, the red, the yellow. I am forced to use green. And as a result, I believe I should get my trophy. Claim your trophy for a correct color scheme. There's my trophy. Yeah. You can collect all the trophies if you want. They got a bunch of other math games down here too, but that's for another day. Go back, I can try it again. I could do polygons. I could do squiggles. Or I could do the United States themselves. Oh, I forgot this was here. I could have easily just brought this up. I don't know why I had to Google anything. But it is impossible to use less than 3 colors. It's been mathematically proven. This website's just a fun little experiment into that. Because of the mathematics behind it. Let me see if I can do this here. I'll make this red. I'll make that red and red since they only share a dot. I'll make that red, 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 red. Try to make as much red as possible. That's not us. That's the old bell. Red, red. And then let me see if I can fill out some green here. Green, 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 green. Ah, undo that. Ah, undo that. Come on, there you go. Green, 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 green. Check. Oh, let me do it with 2. Does that map not work? Ah, the squiggle. Goodness gracious. Something must be wrong with that one. Because you have to use 4. Anyway, I do have a video that I want to show you guys. Click. There it is. Click. So, I have this video talking about the 4-color theorem. That squiggle thing, there must be something going on with that squiggle thing. Because this guy's going to talk about the 4-color theorem in its entirety and what actually this whole thing is about. So I have my speakers set up. I want to play this thing out. I love this math channel, just so you know, Numberphile. It's one of the greatest math channels that's ever existed, but that's my opinion. Let's see what this guy has to say.
So let's talk about the 4-color theorem. It's a favorite with mathematicians. It's easy to state. So the statement is every map can be colored using 4 colors, such that 2 neighboring countries are different colors. That would be confusing if it wasn't. So all maps can be done in 4 colors. In other words, I'm saying there are no maps that need 5 colors. It's not obvious, and you would think more complicated maps would need more colors. But apparently, all maps can be done with just 4 colors or better. So this problem was unsolved.
That's what I messed up. 4 colors or better. That's what I messed up. So you can't go, I'm sorry, you can go 4 colors and you can color everything. You don't need to go to 5 colors. 4 colors is the optimal way that you can color every map that's ever been existed in the history of the world. If you had a map, and I didn't even think about this. But like, here's a map, and here is an island. It's like a singular island. I can just literally color that island red. Boom, 1 color. Yeah. Or if I just had, you guys know about the Haiti and the Dominican Republic? Do you know what they look like? No, it doesn't matter what they look like. But know that in the Caribbean, there is Haiti, and there is the Dominican Republic, and it's literally, this is the island. This is the island, and it's like two neighboring countries. Clearly, you only need 2 colors to do that. So optimally, you can color any map, what this guy is saying, with 4 colors or less. I don't know why I messed that up. I'm going to let him keep talking.
For a long time, 125 years, it was unsolved. It was solved finally in the 1970s, although the method they used to solve it was a little controversial at the time, but has had a large effect on mathematics today. So the story of how this problem came around is kind of cute. Apparently, there was a guy who was trying to colour in the counties of Britain. I don't know why he was trying to do that, but he was, and he suspected he could do it using 4 colours. And he mentioned it to his brother, and his brother was a maths student, and his brother mentioned it to his lecturer, who was a man called Augustus de Morgan. He's a famous mathematician. Well, it was de Morgan who spread this problem around. So to prove it, we either need to show that every map can be done with 4 colours or better, or we just need to find one example that needs 5 colours. So people were trying it. And if you try it with maps, it does work. If you try it with the map of the world, you can colour it with 4 colours. If you try it with the map of the United States, you can do it with 4 colours. If you try any real map, you can do it with 4 colours. I mean, you can give this problem to children, right, if you want to keep them quiet. After a while, you start to think, well, maybe I'll need to invent a map. Maybe if I can invent a weird, complicated map, I can find one that needs 5 colours. So that's what you start to do. It doesn't look like any sort of real life map. So we've got this map, and now we're going to colour it in. So let's start with the middle. I think orange. Next country has to be a different colour. So I'm using the purple here. Let's try the next country. So this is all fairly simple. I can't use purple. I can't use orange because they're touching. I'll use the blue. Next one. What do you want? What do you want, Brady?
Well, we can't use blue or orange. Oh, we could use purple again.
Wise. That is a wise choice. Let's use purple again. Why not? Let's not go to the expense of using a 4th colour. So now let's do this one.
We could use blue again.
And we can use blue again for that one. Excellent. That might put us in a good position when we do the next country. So here we've got, we can't use blue, we can't use purple. What should we use?
Use orange.
We can use orange, why not? Do you want to use orange on the opposite one? So we'll do this one in orange.
And now we need a 4th colour.
We have to go to the 4th colour, do we? Yeah. Purple, blue, and orange are being used. This does have to go into the 4th colour. I've got pink here. On the opposite side, it's the same, obviously. I'm going to use pink over here. It looks like we had to use 4 colours for that. So, okay. So this is a map that was solvable with 4 colours. Here's another important map. I'm going to make it like that. There's only 4 countries. But if we try and colour it in, I'll do something similar. I'll do orange in the middle again. Purple up here. Well, this one can't be purple. It can't be orange. I'm going to use blue. And this country, it can't be orange. It can't be purple. It can't be blue. So I'm forced to use the 4th colour, which is the pink. So this is an example of a map that definitely needs 4 colours. So we're going to boil the problem down a little bit. Let's say I took this map again. I'll draw it here. Same map. Instead of colouring in all the sections, let's just say I colour in at the centre of each region. That'll just give the same idea, won't it? I won't have to use all that in. And maybe, instead of drawing out the whole map, maybe if I just said, if 2 countries are touching each other, they share a border, I'll just connect them with a line. What I've made is I've turned that map into a network. So this map has made this network. And the question, can this map be coloured using 4 colours or better, is the same question as saying, can this network be coloured using 4 colours or better, such that 2 countries that are connected with a line are not the same colour? So it kind of boils down the problem. It makes it more abstract, but that's actually a good thing. It makes it easier to solve. There are things we can learn now about maps by studying networks instead. So the reason we want to use networks, for a start, it shows when 2 maps are the same. I'll show you what I mean. What about if I had a map that looked like this? Yeah, so this map looks like a handbag, as Brady has just told me. But if we draw the network for this map, so I'm just going to put a dot in each region, then I'll connect them if they're connected, like this. You will find that you get the same network as this previous map we did. So it's just 4 countries again. It gives me the same network. It's effectively the same map, even though it looks different. So by studying networks, we can study all the different kinds of maps, even when they look different. Now, all maps make networks, but not all networks are valid maps. I'll show you what I mean. This is not going to be a valid map. And I'm going to say they're all going to be touching each other. They're all mutually touching countries. They all share borders. So it looks like, I got this right, looks like that. Now this is not going to be a valid map, because if you try and turn that into a map, it's not going to work. The problem is the lines cross, which when you try and turn it into a map doesn't make sense. You can try, but it just doesn't make sense. It is allowed if we can untangle the lines, and that might happen. I'll show you what I mean. So let's say these are countries here. And let's say these countries touch each other as well. So I would connect them with a line. But if I do that, you see the lines cross. I don't have to do it that way. I could have drawn a line like that. So I could have untangled that. So if I can untangle it, that's fine. That's a valid map. And by studying networks, there are some features of maps that we can learn by looking at networks. This one in particular, in any map, you're going to have a country. Let's call it A, country A, right? There's going to be a country in every map that's either just by itself, or like an island, or country A is connected to one other country. I mean, that might happen.
About that later.
Or country A is connected to 2 other countries. So you'll get a network that looks like that. That will be country A there in the middle. Or you might have country A, which is connected to 3 countries. This all seems perfectly reasonable. There's A in the center. Country A could be connected to 4 countries. Or, now I'll put A in, or country A could be connected to 5 countries. And that all seems reasonable. But every map will have at least one country that looks like one of these. What you can't have is every country connected to 6 other countries or more. All I'm saying is there's at least one country in that map that's either connected to 1 or 2 or 3 or 4 or 5. But if you have a map where they're all mutually connected to 6 or more countries, that's a network that can't be untangled. So all maps have this feature. One of the country.
Now, I wanted to talk very briefly about the idea of untangling, because we've seen drawings like this before, and when you have these lines crossing over each other, he's saying that can't happen in a map. Let me bring the microphone over. He's saying that can't happen in a map where you have the crossover, but it is possible to untangle it, meaning like for example, this connection right here could be drawn like that. So I untangled that one, and then this one right here, I could redraw it right here. So I untangled that one, and then I only have one more crossover, but I can't untangle that. Because if I tried, like let's say I erased this one right here, and I still have to connect those 2 points, no matter what I'm gonna do, I'm always gonna end up with a tangling. So that's what he's referring to when he says untangling. It's basically redrawing the edge between 2 vertices where they don't cross over each other. And he says that it's actually been mathematically proven, and I want to show this image one more time on the screen. It's been mathematically proven that you actually can have a map where every point is connected to 5 points, is what he's really saying right here. It's really insane to think about it. But you think about it, every single vertex, you could look at every single vertex right here, and it has 1, 2, 3, 4, 5 edges, 1, 2, 3, 4, 5 edges coming out of it. Every point is connected to 5 points. That is the highest that you can possibly go. It's been mathematically proven that you cannot go any higher than that. That is an amazing structure. Anyway, back to this guy.
Is one of these on this list. Now we can start talking about the four-color theorem. This is actually going to be useful. So the four-color theorem is hard to prove, and they tried for a long time. Like I said, it took 125 years. They did manage to prove easier versions of the four-color theorem. So the four-color theorem means there are no maps that need 5 colors. I can probably prove that there are no maps that need 7 colors. That's probably easier to explain. Okay, I'm going to have a go. Okay, imagine there are maps that need 7 colors. These are maps that can't be done with better, right? So there are maps that need 7. Pick the smallest one. Okay, so you've got a small one. Now, because it's a map, it's going to contain a country, which is going to be one of these A's that I've called here on this list. So take that country and put it out. Just delete it, take it away. You've made a smaller map. Now, because it's a smaller map, that means you can do it in 6 colors. Do you remember the map I had was the smallest that had to use 7? So if I take a country away, it's smaller, I can do it with 6. Great. If I put my country A back in, that means I have a spare color to use for A. I mean, the worst case scenario is this last one here. And these could be all different colors. But if I put A back in, I'm still going to have a spare color, a 6th color that I can use, which shows that the map can be done in 6 colors after all. Now, to show that all maps can be done with 5 colors, that's a little bit harder. The proof is exactly the same. The proof is exactly the same, except in this worst case scenario down here at the end here, it becomes harder. Because if those are 5 different colors and you put your country A back in, you might have to reuse a color, which you don't want to do. So the argument's a bit more complicated. You have to show that you can recolor it and you still have a spare color for A. So it's a harder proof, but it's along the same lines. Then they try to do it with 4. Can we show that all maps can be done with 4 colors? And that argument doesn't quite work. It just wasn't strong enough. So this went unsolved for a long time. There were some people who thought they'd proved it. They thought they'd actually done it, and people accepted the proof. And they thought it was solved for a decade. They thought, oh, it's done. And then, they found a mistake and went, actually, that doesn't hold up. And then, oh, no, it wasn't proved. We have to go back to square one. We have to find a way to prove this problem. So it took till the 1970s to solve this problem. So the final solution, it was done by 2 guys, Kenneth Apple and Wolfgang Haken from the University of Illinois. They did it in 1976. It's kind of similar to my proof I mentioned before. They made a list of networks. And they said every map must have at least one of these networks within it. And they showed that every map contains one of these networks. Each one of those networks can be colored with 4 colors or can be recolored with 4 colors. And that is enough to show that every map can be done with 4 colors. Now, it is a hard proof. Part of the problem was having to show that this list could be colored with 4 colors because it was a long list. There were, how many networks was on this list? 1,938 networks. And to do that, they used a computer. And that was controversial at the time. This was the first computer-assisted proof in mathematics. Now it's commonplace. Lots of mathematics is done with computers, but this was the first. And people were wary of this proof. For a start, one of the problems is it involves checking lots of cases. That's not the best kind of proof. It is a proof and it is valid. But the problem with that is it doesn't give you a deeper understanding of why something is true. Just checking lots of cases. Mathematicians do not necessarily like that kind of proof. It's not the best kind, but it's still a valid proof. The proof has been improved. For a start, we had this long list of networks that we had to show we could color in. That got shortened. I think it got shortened to something like 1,400 and something. I think it's shorter now. I'm not sure how short it is at the moment. At the moment, though, the proof still requires this massive checking of cases. So it's still not a beautiful proof.
This episode's been brought to you by Squarespace. Get 10% off your first order with them by going to squarespace.com.
Click. When I first heard of this theorem, I think I was in high school when I first learned about this four-color theorem. The idea was kind of simple. Okay, can I create a map that requires more than four colors? And it just became just not impossible, but just painful, to say the least. So I have something like this. I'm just going to kind of show you this visually for a moment. Let me get some, come on you, get some colors over here. I'll use some red and purple and yellow. Try to make it a bit more obnoxious, and green. There we go. Those are distinguishable. Maybe not the purple. Maybe we'll make a blue. There we go. I'll keep it simple. Like, it's just like the website now. And the general idea being, it's like, well, if I color one of these in, like this one being yellow per se, you can see that quite clearly. Then the logic dictates that it's like, well, then this one can't be yellow. Well, let me see. Well, okay, then this one right here can't be blue or yellow. This one can't be blue or yellow. The idea being, okay, am I required to use more than four colors? If I do less than four colors, we're fine. This one can't be, well, I'm going to make this one green for fun. And now over here, I have to pick, well, again, I could pick like a fifth color, but in reality, I don't need to. I could just make this one red. There's no reason why I shouldn't make that red. And then same thing over here. I could make this one green. I could make this one blue. I mean, I could make this one red. And then if I made this one red, then I would be forced to make this one green. And if I made this one blue, then I would be forced to make this one red. Nah. Fine, I'll make it blue. And now I have an option here. I can make this either red or green, actually. So I'll make it red. But then this outer little country right here, I got to make it yellow. I have to make it yellow because that outer country does indeed cover red, blue, and green all at the same time. Well, like I said, there are people who thought they had proven this theorem, but there were mistakes made along the way. People who thought, like, look, here's a map that requires 5 colors. And it's like, well, no, just switch this and this, and then you got it. It's fine. You could use 4 colors. It is possible to use 4 colors on this stuff where you have no bordering things. Now, I show you this, and then I show you this. Now, we're not going to do this one today, but this is a partial map. This is a partial map of Europe. I think the Czech Republic changed their name. Doesn't matter. Don't care. But this is a partial map of Europe. And believe it or not, this map of Europe and this circular-ish map right here are the exact same map. They are the exact same map. I can show that. For example, Austria right in the middle. That's my middle junction being a little yellow right there, junction right in the middle, bordering Germany, the Czech Republic, Slovakia, Hungary, Slovenia, Italy, and Switzerland all at the same time. The only one that it's not bordering up here is Poland, which is the other yellow color. And then you can see the Poland is actually bordering Germany, Czech Republic, Slovakia, which I could color in like that as well, where Germany would be this red, and Italy would be this red. My marker's dying on me. Yeah, it's totally dying on me. And I'm a little out of time, so I'll have to finish this next time. But my point being, though, is that the maps that we draw on here can easily be reconfigured. We'll pick up with more of this on Thursday. Don't forget your projects, and we'll talk on Thursday. If you have not left a comment in the chat, please make sure that you do so. Everyone's going to be traveling to second period. Woo. And then I don't know what's happening from there, but we'll see what happens. I'm going to sign off. Have a good one.